Okay, folks, this is chapter 3-2. This is recording number 5. All right, so Chebyshev's theorem is a way for us to decide ahead of time, or to determine ahead of time, what proportion of the values from a data set, what proportion is it 5%, is it 10%, is it 20%? What proportion will fall within some number of standard deviations of the mean? Okay, so this has a lot of utility, a lot of usefulness. It's used in a form of artificial intelligence that I worked on when I was working as a consultant with the Air Force. We didn't call it artificial intelligence back then. We called it pattern recognition, and the goal was to be able to identify targets based on their radar cross section, as an example. So you could tell a decoy from a real nuclear device. Okay, and so we would be able to use Chebyshev's theorem. We would be able to make a decision. We called it discriminate. We would be able to discriminate between targets. We'd say, is this thing that we're looking at, is it a true, what's called a reentry vehicle? Is it a true reentry vehicle, or is it a fake? Is it is it a decoy? And we would use Chebyshev's theorem, would be one way of doing it, because you'd have the data and you would say, well, does this fall within a certain percentage or a certain number of standard deviations of the mean? So I'm not trying to explain to you how we did it, okay, but I'm just trying to give you an example of where this is very relevant. You could also use it for other contexts if you wanted to try to find out if what you're looking at is a certain type of a certain type of a species that you're looking at based on the information. You can look at various signals. Well, how about in medical contexts? If you can look at X-rays and you can try to decide, is this a tumor or is it not a tumor? You would be able to figure these things out. Is it within a certain standard deviation of the mean? Okay, so you classify it. It's called a classification algorithm. It's a very, very important part of artificial intelligence. And as an example, I used it when I was working for the Air Force, and nowadays artificial intelligence people use it to come up with algorithms for classifying medical conditions. Is this a tumor or is this not a tumor? Okay, so I'm trying to make it relevant for you, because some of this stuff looks like, oh my gosh, why are we learning this? So I'm trying to convince you that it is very, very relevant. Okay, so here's the theorem. I'll let you read that yourself. Let me just try to help you understand it. This K, what the heck is K? It's within K standard deviations. K is not necessarily an integer, but I think most of us kind of think of it as being an integer, like 3, okay? So let's use 3. The proportion of values from a data set that will fall within 3 standard deviations of the mean will be at least 1 subtract 1 over k squared. So 1 over k squared would be 1 over 3 squared. That's 1/9. So 1 subtract 1/9, that's 8/9, right? Yeah, 1 subtract 1/9, it would be 8/9. So whatever the heck that is, I'll get my calculator out. 8/9 is 0.888, so that's multiplied by 100, that's 88%. Let's round it up to 89%. Okay, so the proportion will be 89% would be within 3 standard deviations of the mean. And the only requirement here is that k has to be a number greater than 1. Greater than 1. Now, why does it have to be greater than 1? Because look what happens. If you make k 1, it's 1 over 1 squared. Okay, 1 over 1 squared is 1, so 1 over 1 is 1, so 1 subtract 1 is 0. Well, how can you be within 0 standard deviations? It doesn't even make any sense, right? Okay, so I gave you my example, but let's take a look at the book's example. Let's use 2, if k is 2. So 1 subtract 1 over k squared, that's 1 over 2 squared, so that's 3/4, that's 75%. So what they're saying is that, hey, listen, at least 3/4%, it could be even more than that, but at least 3/4% will fall within 2 standard deviations of the mean of the data set. Okay, so you plug that in and boom, there you go. So now let's take a look at a concrete example. Let's say you have a variable, whatever it happens to be, whatever the variable happens to be, say it has a mean of 70, has a standard deviation of 1.5, and you want to know all right, so you have the 2 standard deviations. Okay, we just told you that we just said that 75% of the data values will fall between the mean plus or minus 2 standard deviations. Okay, I think it's best to look at a cartoon before we get into the numbers here. Let me look at this cartoon here. It's a little bit further down the road. Okay, so here's kind of a cartoon. Here's my X bar. Here's X bar plus 1 standard deviation right there. Here's X bar plus 2 standard deviations. So if this is the X bar, here's 1 standard deviation, here's 2 standard deviations. Okay, so that's what we're looking at here. We're adding and subtracting 2 standard deviations. Okay, so going back up here to this where we left off, you add or subtract 2 standard deviations. So in this particular example, it has a standard deviation of 1.5, okay? So, and the mean is 70. So 70 plus 2 times 1.5 is 70 plus 3, which is 73. And then X bar subtract 2 standard deviations, it would be 70 subtract 3, which is 67. Okay, so between 67 and 73, okay, that's the 2 standard deviations on each side of the X bar. How much of the population is going to be in there? Okay, we know from Chebyshev's theorem at least 75% will be between 67 and 73. Okay, the second example that he was giving you there, okay, it will be 75% will fall between, he says, 50 and 90. Where did we come up with that? Well, it's 70 plus 2 times the standard deviation and 70 subtract 2 times the standard deviation. But this time the standard deviation is 10, not 1.5. That was the example that he was giving right here. Okay, so 70. The first one has 70 and a standard deviation of 1.5. The next one has 70, but it has a standard deviation of 10. Okay, so work your way through that example. You know, pencil and paper in hand, just reading it, it never is satisfactory. You've got to work it out yourself. You've got to write it out, and you got to put in as much detail as you need to understand it. I hope I helped explain here a little bit. Okay. All right, the same idea here within 3 standard deviations. Where do we come up with the 3 standard deviations? That's the example I just gave you. It's 1 subtract 1 over k squared, so that's 1 subtract 1 over 3 squared. That's the same as 1 subtract 1/9, that's 8/9, so that's 88.89%. Okay, so again, it's like how much of it will be between there? It's 70 plus 3 times the standard deviation. Okay, that gives me this upper bound, and then 70 subtract 3 times the standard deviation gives me the lower bound. So between 65.5 and 74.5, there's going to be at least 88.89% of the data values for that first example that he gave, a mean of 70 and a standard deviation of 1.5. Okay, all right, so you know, if you crank out these numbers here and you like you say, well, okay, within 2 standard deviations, within 3 standard deviations, how much of the data is going to be there? Here's an arbitrary distribution. It doesn't have to be a nice, well-behaved distribution. It doesn't have to be bell-shaped. It's any distribution. Okay, you've got an X bar, and you say, well, when I go 2 standard deviations, so here's 1, 2, or I go 3 standard deviations, so here's 1, 2, 3 standard deviations. How much of the data is between, you know, plus or minus 2 standard deviations, plus or minus 3 standard deviations? Well, it's at least 75%, and it's at least 88.89%. See, that's what these lines up here are telling us. Okay, now I'm calling these cartoons because, you know, it's a histogram, right? And it's there's no particular values in here, right? It's just a visual aid. The key here is you go from X bar, you go either 2 standard deviations or you go 3 standard deviations. How much of the data is between plus or minus, or within the interval plus or minus X bar plus 2 standard deviations, X bar plus or minus 3 standard deviations. So it's a cartoon. It's not intended to be analytical. I can anticipate a question that someone might ask. They might say, well, wait a second. You go for X bar, and then you go here to X plus 2S, you know, X bar plus 2 standard deviation, and here it's X bar plus 3 standard deviation. This distance here is a lot bigger than this distance here. Well, why is that? Well, it's because it's a cartoon. He doesn't include the X bar plus 1 standard deviation. Your imagination has to put that in here. So here we are at 1 standard deviation away from X bar. Here we are 2 standard deviations away from X bar. Here we are 3 standard deviations away from X bar. And the same thing in the other direction. Okay, so I hope that helped you. All right, so here we go. Here's an example. I'm going to let you work your way through this. I swear all you got to do is take your pencil and paper out, you know, and write it down step by step, and it's going to become abundantly clear. Okay, so this next concept here is illustrated by example 3-26. So I'm going to put that on the next video because I'm running out of time, and there is a little bit of a nuance here that I think I need to explain to you to help you out. So this is the end of this video.